Hiyama coupling, also known as the Hiyama cross-coupling reaction, is a palladium-catalyzed carbon-carbon bond formation reaction that involves the coupling of organohalides and organosilane. This reaction was developed by Professor Tamejiro Hiyama in 1988 and has since become an important tool in synthetic organic chemistry for the synthesis of various compounds. In Hiyama coupling, a palladium catalyzed coordinates with both the organohalide and organosilane, leading to the formation of a reactive palladium intermediate. This intermediate then undergoes reductive elimination, resulting in the formation of new carbon-carbon bond between the silicon and the halogen substituents. One important application of Hiyama coupling is the synthesis of pharmaceuticals. For example, the coupling has been utilized in the synthesis of the antifungal agent. Researchers also use this method to construct complex molecular frameworks found in drugs such as HIV protease inhibitors, anti-inflammatory agents, and antiviral drugs. Another example of the application of Hiyama coupling is in the medicine. It's used in the synthesis of anti-cancer agents. For instance, researchers have utilized the Hiyama coupling reaction to synthesize novel aryl silane derivatives that exhibit potent anti-proliferative activity against cancer cells. An example product of Hiyama coupling is the synthesis of bipennyl compounds. For instance, the reaction of ionobenzene with trimethylsilyl bromide and a palladium catalyst in the presence of base yields 4-trimethylsilyl bipennyl as the product. The reaction mechanism involves the formation of an aryl palladium intermediate which then reacts with the organosilane to form a new carbon-carbon bond. An example product of Hiyama coupling is the synthesis of bipennyl compounds. For instance, the reaction of ionobenzene with trimethylsilyl bromide and a palladium catalyst in the presence of base yields 4-trimethylsilyl bipennyl as the product. The reaction mechanism involves the formation of an aryl palladium intermediate which then reacts with the organosilane to form a new carbon-carbon bond.
Next is the advantages and disadvantages of Hiyama coupling. The first advantages of Hiyama coupling is high selectivity. The Hiyama coupling reaction is highly selective, allowing for the formation of specific carbon-carbon bonds while avoiding unwanted side reaction. The second advantages of Hiyama coupling is versatility. The reaction is compatible with a wide range of functional groups, making it a versatile tool for the synthesis of complex organic molecules. The third advantages of Hiyama coupling is high efficiency. The reaction proceeds with high efficiency, yielding high product yields in a relatively short amount of time. The other advantages of Hiyama coupling is Hiyama coupling can be carried out under mild reaction conditions, minimizing the formation of unwanted byproduct and reducing the need for the harsh reaction conditions. Next is the disadvantages of Hiyama coupling. The first disadvantages of Hiyama coupling is Hiyama coupling reaction require the use of expensive palladium catalysts, which can make the reaction costly. The second disadvantages is sensitivity to air and moisture. The reaction is sensitive to air and moisture, which can lead to the degradation of the reagents and reduce reaction efficiency. The third disadvantages of Hiyama coupling is toxicity. Some of the reagents used in the Hiyama coupling reaction can be toxic and hazardous to handle, requiring special safety precautions. And then the other disadvantages of Hiyama coupling is the reaction may not be suitable for all substrates, as some functional groups may be incompatible with the reaction conditions. The general equation for the Hiyama coupling can be shown on the poster, where organic groups. X is a halogen atom such as chlorine or bromine, and SiR3 is an organosilicon compound such as 3-methylsilyl or 3-ethylsilyl. The reaction is catalyzed by a palladium catalyst, typically a palladium complex, and a base such as a carbonate or a hydroxide, and it is often used to deprotonate the silane and promote the reaction. The Hiyama coupling is a useful method for the formation of carbon-carbon bond and has found application in the synthesis of a wide range of organic compounds. The Hiyama coupling reaction is a type of cross-coupling reaction that involves the reaction of an organohalide with an organosilicon compound in the presence of a palladium catalyst. The reaction occurs in several steps. The first step is the activation of the palladium catalyst. The palladium catalyst, typically a palladium complex, is activated by a base such as carbonate or hydroxide. The second step of the reaction is the formation of the organopalladium intermediate. The organohalide and organosilicon compound react with the activated palladium catalyst to form an organopalladium intermediate. The halide group of the organohalide is replaced by the organosilicon compound to form a new carbon-silicon bond. The third step of the reaction in Hiyama coupling is the reductive elimination. The organopalladium intermediate undergoes reductive elimination to form the final product. The reductive elimination step involves the breaking of the carbon-palladium bond and the formation of new carbon-carbon bond. One example of Hiyama coupling reaction is the coupling of an aryl halide and an organosilane using a palladium catalyst. This reaction can be catalyzed by a palladium catalyst in the presence of a base such as potassium carbonate. This reaction proceeds through oxidative addition of the palladium catalyst to the aryl halide, followed by transmetallation with the organosilane and reductive elimination to form the desired product. The reaction is typically conducted in anhydrous condition and at elevated temperature. For the conclusion of this video presentation, Hiyama coupling is a valuable tool in organic synthesis which has been widely used in the creation of carbon-carbon bonds. It offers several advantages over conventional coupling reactions, such as its mild reaction conditions, high yields, broad substrate scope, and compatibility with a wide range of functional groups. Hiyama coupling has been successfully applied in the synthesis of many biological active compounds, natural products, and pharmaceuticals. However, there are still some challenges that need to be addressed, such as the development of more efficient catalysts and the optimization of the reaction conditions. Despite these challenges, Hiyama couplings remain an important technique in a modern organic synthesis and is expected to continue to play a significant role in the development of new drugs and materials in the future.